Hi dear students, today we will discuss about compensators used in the case of control system design. First of all, let us see what do you mean by compensation. See, compensator is a device inserted into the system for the purpose of satisfying the desired specifications. So, such a redesign or addition of a suitable device is called a compensation. So, we will be given a system and the system we should design a linear system with the desired specifications. So for designing such systems we will insert some components and sometimes the specifications will not be attained by a particular design, so we have to redesign the system by adding different components, and such process is called compensation. And compensator basically introduce pole and zero, sometimes it may be a pole or zero, in open loop transfer function to modify the performance of the system. The compensation schemes used for feedback control system is either series compensation or parallel compensation. In the case of series compensation, the compensator with the transfer function Gc of S is placed in series with the plant. That means we will place a series compensator, or we will place a transfer function which represents the compensator in series with the open loop transfer function. That is what is called planned. And in the feedback compensation, the signal from some element is fed back to the input, and a compensator with the transfer function Gc of S is placed in the resulting inner feedback path. We can see the configuration C. Figure shows the series and feedback compensation, and in the first you can see that the compensator with the transfer function Gc of S is placed in series with the open loop transfer function Gc of S. In the second case, here the compensator will be placed in the feedback path, but it is not in the original feedback path where signal is fed back, but it is placed in the inner feedback path. Okay. The compensator may be electrical, mechanical, hydraulic, pneumatic or other type of device or network. The different types of electrical or electronic compensators used are lag compensator, lead compensator, lag lead compensator. So we will study about these three types of compensators. First one is lag compensator. Usually the lag compensator has got the characteristics of a lag network, that it provides lag in the design, and basically if we are designing it will if you are designing it in the electrical network, then it will function as a low pass filter, and the attenuation due to this lag compensator shift the gain crossover frequency to a lower frequency point. See, here now we will discuss about the frequency domain approach in the compensation case. So we will design the lag compensator with the help of border plot. So that case it is seen that the attenuation due to this lag compensator shift the gain crossover frequency to a lower frequency point. And usually this compensator provides or inserts 0 or poles to the transfer function. So the 0 of the lag compensator is given by Zc is equal to 1 by T, and the pole of the lag compensator is given by Pz is equal to 1 by beta T. Here T will be greater than 0 and beta will be greater than 1. And the transfer function of the lag compensator will have the form Gc of S will be equal to S plus Zc divided by S plus Pc. Zc is the 0 of the lag compensator, Pc is the pole of the lag compensator. So that will be equal to S plus 1 by T divided by S plus 1 by beta T, where T greater than 0 and beta greater than 1. Usually the realization of the lag compensator usually using electrical network is shown in the figure. It is a series combination of two resistors R1 and R2 along with the capacitor C, and here S domain representation is shown. That is why we are taking, instead of C we are using 1 by Sc, and EI of S is the input voltage and E0 of S is the output voltage. And if we are realizing the compensator in this form, then the transfer function E0 of S by EI of S will be in the same form as S plus Zc by S plus Pc. So next let us see the procedure for the design of lag compensator using border plot, and it is an important thing. You should go through the procedure step by step. There are 9 steps for designing the lag compensator using the bode plot. So first step is, see, in the question we will be given by a transfer function, that is open loop transfer function, that is g of s. So in that, sometimes the k will be, there is some variable k. So first of all, what you have to do is choose the value of k in uncompensated system to meet the steady state error requirements. So you will be given a question to satisfy some conditions. So there will be some requirements. Sometimes there will be some steady state error requirements, or sometimes there may be some phase margin requirements, like that. So first of all, you will be given an open loop transfer function g of s that will be representing the uncompensated system, and you are asked to find the compensated system. So first you have to choose the value of k in uncompensated system to meet the steady state error requirements. So, and after getting the value of k, you have to plot the border plot corresponding to the uncompensated transfer function in the semi-log graph. So second step is sketch the bode plot of uncompensated system. You know that for plotting the bode plot, you have to plot magnitude plot and phase plot. So it will take some time because it has some procedure, and it is discussed in the previous videos. That is for plotting bode plot. There has some steps you have to go through that steps. Go through that steps, okay? And you need a semi-log graph, and you have to plot both the magnitude plot and phase plot on the same graph sheet. Third step is, after plotting the bode plot, you have to determine the phase margin of the uncompensated system from the bode plot. So phase margin is corresponding to the phase corresponding to the gain crossover frequency. It has got an equation gamma equal to 180 plus 5 GC. So you have to first mark the gain crossover frequency and then corresponding phase, and you can find out the phase margin. And if the phase margin does not satisfying the requirement, then the lag compensation is required. See, you will get a phase margin from this step. So in the question, you have to attain a particular phase margin. You have to verify whether your phase margin is equal to the phase margin given in the question. If it is not satisfied, then you have to go for lag compensation. Okay, so next step onwards, you will know how to design a lag compensator. For that, first of all, you have to choose a suitable value for the phase margin of the compensated system. So that is up to you, that you have to choose a particular phase margin. See, gamma d is the desired phase margin as given in the specification. That means it is given in the question. That is, gamma d will be the desired specification. See, gamma n is the phase margin of the compensated system. So gamma n will be equal to gamma d plus epsilon, where epsilon is the additional phase lag to compensate for shift in the gain crossover frequency. So you have to choose an initial value of epsilon, that is 5 degree. So you have to add it with the gamma d. See, gamma d you have calculated from the previous step. Gamma d you will get it from this step, and you have to add 5 to that gamma d so that you will get gamma n. In this step 5, you have to determine the new gain crossover frequency 5 GZN. So once you get gamma n, there will be a corresponding gain crossover frequency. So you have to determine the new gain crossover frequency, that is represented by 5 GZN, and the new omega GCN is the frequency corresponding to the phase margin gamma n on the bode plot of the uncompensated system. See, now you have a bode plot corresponding to an uncompensated system. So you have to mark the 5 GCN corresponding to this gamma n on that bode plot. Once you mark this 5 omega GCN, you will get gamma n from that plot itself. So you can find 5 GCN, that is phase of G of j omega at a new gain crossover frequency omega GCN, and you can find gamma n equal to 180 plus 5 GCN. So 5 GCN will be obtained from this equation, that is gamma n minus 180 degree. So you will get the new phase. The new gain crossover frequency omega GCN is given by the frequency at which the phase of G of j omega is 5 GCN. That is its meaning. And the next, once you got the new gamma n, new 5 omega GCN, you can determine the parameter beta using the equation. You have A GCN equal to 20 log beta. And beta can be obtained from this relation as beta will be equal to anti-log AGCN by 20. So determine the parameter beta of the compensator. The value of beta is given by the magnitude of G of j omega at new gain crossover frequency omega GCN. So find the dB of AGCN at new gain crossover frequency omega GCN. So AGCN can be found out by 20 log beta. From this equation you can find the value of beta. So you will get beta. See, what is your goal is to find the lag compensator transfer function. You know that in the lag compensator transfer function it has a form. You know that it has got the form like this. See, this is its form. See, this will be its form. Okay, so you have to find out the value of beta in order to find out the GC of S. Okay, so here once you get the beta, you can go to the next step, that is step 7. You have to determine the transfer function of lag compensator. For that you have to place the 0 of the compensator arbitrarily at 1/10th of the new gain crossover frequency. Now you have the value of omega GCN from the previous step. So 0 of the lag compensator, you know that it has got the form ZC equal to 1/t, and it is obtained, 1/t value is obtained by 1/10th of omega GCN. So omega GCN by 10 will give the value of ZC. Now you can find out the value of T. T will be equal to 10 by omega GCN. And next you have to find out the pole of the lag compensator. Pole will have the form Pc equal to 1 by beta T, and you can find the beta value you got from the previous step, that is beta you will get from here, and T you will get from this step. So you can find out the pole Pc, so that the transfer function of the lag compensator is equal to S plus 1 by T divided by S plus 1 by beta T. It will have a form beta into 1 plus St by 1 plus S beta T. So this transfer function, that is compensation transfer function, will be provided with the open loop transfer function in series connection. So you will have the block diagram of the lag compensator like this, that is 1 by beta in series with the beta into 1 plus St by 1 plus S beta T into G of S. So this is the here G of S is the open loop transfer function that is given in the question. Now for the getting the desired phase margin, you have to add this compensation network in series, and here the feedback path will have got the value of 1. So this is the block diagram of the lag compensated system. So now you get the block diagram of the lag compensated system. Next you have to check whether this system satisfies the desired specification. So determine the open loop transfer function of the compensated system. The lag compensator is connected in series with the plant as shown in the figure. When the lag compensator is inserted in series with the plant, the open loop gain of the system is amplified by a factor beta. Here beta is greater than 1. And if the gain produced is not required, then attenuator will with gain 1 by beta can be introduced in series with the lag compensator, that is to nullify the gain produced by the lag compensator. The open loop transfer function of the compensator system is given by G0 of S is equal to 1 by beta into Gc of S into G of S. That is equal to 1 by beta into 1 plus St by 1 plus S beta T into G of S. So you will get 1 plus St by 1 plus S beta T into G of S. So next in this step, 9th step, you have to determine the actual phase margin of the compensated system and calculate the actual phase angle of the compensated system using the compensated transfer function at new gain crossover frequency omega GCN. So phi GC for the open loop system is equal to phase of the G0 of j omega at omega equal to omega GCN, and here then you can calculate the actual phase margin of the compensated system gamma 0 is equal to 180 plus phi G0. So now you will get y0. You have to check whether this gamma 0 is equal to the desired compensation given in the question. Okay, if the actual phase margin satisfies the given specifications, then the design is accepted. Otherwise, repeat the procedure from step 4 to 9 by taking epsilon as 5 degree more than the previous design. Okay, so now you have designed the system with the epsilon equal to 5 degree, and you have gone through different steps, and at last you will reach the step 9, and in the step 9 you have to calculate the gamma 0. If the gamma 0 is equal to the gamma 0 given in the question, then you can stop the procedure there. If gamma 0 not equal to the phase margin given in the question, then you have to go to the step 4 where you have taken epsilon equal to 5 degree. But if it is not satisfied, then you have to take epsilon will be equal to 10 degree, and you have to continue the procedure from 4 to 9. Okay, that's all about this lag compensator design. Next you can do a problem, and you will understand the steps clearly when you are doing a problem. Okay, thank you.